Hello, on behalf of TOS International, I'd like to welcome you. My name is Peter Rittmeyer. In this presentation, we're going to talk about uniform pressure airbag modeling. A few parts of gas flow will be addressed as well, but the prime part will be uniform pressure, although I must admit that it's also applicable for gas flow. One warning, don't be shocked about the next slide because it contains some of the equations used for the thermodynamic analysis taken from the theory manual. Probably from high school you remember the ideal gas law. Pressure times volume is equal to the mass times the gas constant times the temperature. It's an ideal gas law. For airbags this is valid. Only if you get into extreme pressures this ideal gas law is not applicable anymore. So the ideal gas law is the basis for uniform pressure and as well gas flow calculations. The next equation is a very long one. I'm not going to explain all the details. It's an energy equation of airbag chamber. I said deliberately a airbag chamber because you can define more airbag models in one model of MADYMO. That can be either a passenger airbag and driver airbag or curtain. Those are typically modeled in one FE model separately. However, it's also possible to define one airbag, for example a torus head airbag, out of multiple airbag chambers. That's also where this makes this equation slightly longer. It deals about mass inflow, the enthalpy brought into by the inflator, outflow, heat losses, kappa, as it is addressed, the work done term, some energy losses by global discharges. That is what this equation is all about. The next slide, we're going to talk about the term cycle. It's defined under control airbag, as you can see in the example right in the right bottom. It's set to 25. This is generally a good model. But what does this value mean? It's a thermodynamic subcycling with respect to the FE time step. It means that in one FE time step 25 thermodynamic calculations are performed. Those calculations hardly consume any CPU. It's a simple, straightforward Euler integration and it makes your simulation much more accurate, especially if you have larger FE time steps. You can define a higher value if you like, but that generally won't affect your results. However, if you put it to 1, you probably might see differences in results. So it's something like a convergence. For gas flow, it's slightly different. Gas flow has its own time step, which depends on the size, so the cell size, the temperature and the velocity. Those are all make together the gas flow time step. Well, MADYMO takes the minimum of the FE in the gas flow, so there is no subcycling between FE and gas flow. However, it's still possible to have other subcyclings. For that, let me please explain the table on the left bottom. It's a snapshot of a simulation. It could be either a thermodynamic, or so let's say a uniform pressure calculation, or a gas flow calculation. It's even possible to apply both in one simulation. On top, the output time step is just one time step, written out to the output time step files. The multi-body time step contains 4 time steps in one output time step. In this case, the FE time step is the same. The TD, so the thermodynamic cycle, is 25 with respect to the FE. And gas flow is equal to the FE time step. In principle, it's possible to have subcycling between MB and FE. So the MB time step can be, for example, 1 in this case, just equal to the output time step. And it is a factor of 4 difference with the FE time step. However, this is not recommended to be used because it can induce extra noise on your signals. because the MB time step is only updated once, and in the same time 4 FE time steps have been formed. One of the ways to prevent subcycling between MB and FE is making use of the use FE time step on under control analysis time. Another way is to define a lower time step under control analysis time as well, because the time step defined under control analysis time is the MB time step. You can always check in your reprint file where you have subcycling between MB and FE. Under control airbag, more things are defined. So not only the term cycle, but also, for example, the pressure and the temperature in the ambient. So that's not within the airbag. However, during initialization, so when the airbag is not triggered yet, the ambient condition is also applicable within the airbag. You can define the gas pieces of air, for example, or if you would like, other properties, although this is not very likely. There are default values defined for air, so those you don't have to define, but defining them doesn't matter. Well, now let's go to the next slide. It's about airbag chamber. That is basically where you define the airbag. You have to define a group list that contains all the parts or elements that make together a closed surface. It might be possible that you would like to have to define holes. Those can be defined in two ways. They will be addressed later on. You can define holes under the airbag chamber, and then MADYMO will close them automatically. The other way, probably more flexible, is by defining them by parts. But as said, this will be addressed later on in more detail. Also already addressed is that you can define multiple airbag chambers. For example, a head-thorax airbag. And then you can link them together and there will be gas exchanged between those two chambers and also to ambient. There are a few other things which you have to define. Auto volume on. It ensures you that the normals are pointing in the right outward direction, because that is the direction where the pressure is applied on. And the pressure is applied on the element that is transferred to neutral forces. On top of that, you can also define a chamber V0. It's the physical volume which you haven't modeled, for example, the inflator house volume. If you don't need it, it's better to define it to 0. Don't leave it undefined. That's typically recommended if you're going to simulate tank test analysis. Always check in your output whether the volume at the initial state or during the deployment makes sense, such that you are sure that you haven't made any errors. Well, now let's go to the mass and energy on the next slide. Here you see a simplified example of an airbag. It contains two chambers. In the left there's an inflator and it has its own state, so pressure, volume, mass, temperature, and there are defined a few holes. But it can also be a permeability, and due to those holes and permeability, gas can flow from chamber 1 to chamber 2. If there are no special precautions taken, it's also possible, in case the pressure in airbag chamber 1 is lower than airbag chamber 2, that the flow will be the other way around. In this case, only the second chamber has outflow to ambient. Obvious, it's also possible to define holes and permeability for the airbag chamber 1. Well, how does the mass of an airbag chamber looks like? I should say the mass flow rate. It's the sum of the supplied gas from the inflator plus the incoming gas of the other chambers. And from that, the exhausted gas mass is subtracted. So the total mass flow rate will be the mass flow through the pores, the vents, and the global discharge. That will be addressed later on what the global discharge is. But I think pores and vents, they explain themselves. It's also possible to have heat loss. And that's what we call the kappa. Also to be addressed later on in another slide. Inflator and jet. Initially, there is no extra gas of the inflator in the airbag chamber. That has to be brought into the system by an inflator. You can define it in several ways, but basically they are all the same. You have to define the moment of triggering, so when the gas is brought into the system, you have to define a mass flow rate and a temperature function. There are a few others as well possible, but those are commonly not used. Typically, this information is provided by the inflator supplier. If there is no data available, use can be made of the MTA analysis tool, one of the tools provided by the MADYMO release package. Besides the mass flow and temperature, there is also a gas mixture definition. That is the gas brought into the system by the inflator. So that's not generally air. That can be constant in time or can even be variable in time. Under the inflator, you can also define a jet. In this case, you see a jet idle chick. It's applicable for uniform pressure only. Uniform pressure simulations don't require a jet, but it might be beneficial to use it. For gas flow, you can't apply an idle chick, but it will be a jet gas flow. This gas flow jet is required, because otherwise you can't bring the gas of the inflator into your airbag system, because it's located outside and there won't be any active gas flow cells. If you like, you can even define multiple jets per inflator. Obviously, you can also define more inflators if you like. Per inflator, the distribution over the jets is based on the jet area. Here you see a little bit more information about those jets. In the most top you see a jet cone, and let's assume it's an idle chick jet. First thing which is seen is that the jet is inside the airbag. Then there is something like a cone, a MADYMO loop to which elements it has to apply an extra force due to jet. This is an empirical based jet, and that is what you see in the next picture. So under the jet cone picture, you see something like a Gaussian curve. That's the velocity which is used for calculation at the end for the jet forces. The further it's away from the jet, the lower this velocity profile will be. So the effect of the jet will be less if the distance is increasing. You can define two shapes, either a circular or a rectangular outlet, where you see the pictures given on as well here. In total, 4 types of jets are available. Most commonly used in uniform pressure is the idle chick. For gas flow there is only one available. Let's focus a little bit more on the jet idle chick. Here you see an example. You can attach it to a body. Suppose you would like to let it move into space. But you can also apply it or attach it to the reference base. You have to define a jet center location and a direction. If you like, you can define a specific group of elements where it's working on. Obvious, this element list or group list has to be part of the airbag chamber. Maybe of most interest is the efficiency factor. It can be defined in several ways, but it basically means that you can temper or make it more aggressive, this jet, even in time. Let's move on to the permeability models. There are a lot of them. Most commonly used is Permeability Model 1 and Permeability 2. There are tests available in industry, by which you can derive the values to be filled in for those permeability models. Maybe of interest is that you also see sometimes a function which is a function of time. That might look strange. The reason for that is, typically for uniform pressure, is that you would like to control the outflow in time. For permeability that maybe doesn't make that much sense, but for holes it's maybe more easy to understand. If you have a voltage airbag, holes might be not directly active because they are closed, because there is no gas located there. However, if you're going to apply uniform pressure, the pressure will be everywhere the same inside the airbag model. And for that reason you will get directly outflow, although physically it might not be the case at that moment. Defining a time step function, you can control that more. So for example, the first 10 milliseconds there is no outflow possible, because you put the time function to 0, and gradually you can let it grow to 1. Vents, or holes if you like. As already said, you can define them in two ways. You can define them under the airbag chamber, or you can make a separate part of them. 3 models are available. The third one is applicable for gas flow only, and then only between 2 chambers, not to ambient. Most commonly used is the hole model 1. If you're going to define it under the airbag chamber, it will create segments. They look pretty much similar to elements, but they have a different characteristic. Basically, they don't have any stiffness. If you're going to define it like a part, it will get some stiffness. If you do that, you have to take some things into account. Actually, to some extent it also accounts if you make them automatically. The most left picture, with the green tickle, that is the way you should model it. Whether you do it automatically or manually. It doesn't have any nodes of the hole within the hole itself. The hole nodes are only at the edge, so let's say at the fabric side. The middle picture is a way you shouldn't define it. There you have extra elements, so nodes not at the border of the fabric. As the elements have either no or very low stiffness, you might end up into instabilities. If those nodes are flying far away, you will end up also in a large area of your hole, and due to that the outflow will be wrong. The third picture is something which MADYMO can't capture at all. So best is to do it in the most left picture, as you can see. This is the most robust approach. If you're going to model holes by parts, you have the possibility to define hole characteristics per part. If you're going to do it in the airbag chamber, all holes, if you have multiple of them, will have the same characteristic. There are 2 attributes which have to be explained more into detail. That is the stiff and min step. Although I would say the min step you can forget in general always, but they require simply a little bit more explanation. Stiff. It's an artificial stiff parameter. By default it's 100 Newton per meter. It's much lower than the E modulus of the fabric in general. However, if you have extreme skilled airbags, for example if you have a multiple chamber where things are skilled, the area of the hole, the exchange hole, can grow tremendously, and even such a value of 100 can require a lot of energy to let it grow to his, let's say, deployed state. And maybe the energy is not even available, and then you can end up in something what we call necking. For that, it's generally better to define a value of 1e minus 2. In those cases you will probably have no necking. It's simply to check by looking to your animations. The min step is something to do with mass. If you going to make whole elements by parts, they will get whole material properties. As you can see, and that's the stiffness value basically. As it has stiffness, and there are some other default values defined, it will also get some mass. And that might introduce mass scaling. However, from experience it's noticed that the default value for that is generally sufficient. Now let's focus more on the whole models available. As said, there are 3 models available, 1, 2 and 3. Although 3 is only for gas flow. Most often used is the whole model 1. It's a 1D quasi-static isotropic approach. There's a lot of words, but basically means that the outflow velocity is everywhere the same in the hole, which of course is not the case. You will have boundary effects, and due to that you have a more like a Gaussian shape velocity profile. Well, you can correct for that by the CDEX value, as you can see in this example. On top of that, the CDEX is an outflow correction, but it can also be that you can use this as a correction of the correlation between the hardware hole and the model hole, because it might well be that the hole in the physics is not the same as you have modeled. Well, you have to make a compensation for that as well. That's also done in the CDEX. So you might end up in a multiplication of 2 values stored in one CDEX value. Besides that, you have, as already said, a time function for the whole outflow, but there is even more, like triggering when the hole starts to open or to close. All those things can be found in more detail explained in the reference manual. Block flow. It's a value between 0 and 1. 0 means it doesn't matter where you have contact or not, the outflow will remain the same. If it's 1, then you are at the other side. If there is contact between such a whole element, but it can also be permeability, there will be no outflow. It's a user-defined value, and typically it's in the range of 1. You can define it on 2 locations, under the control airbag or under the whole or permeability models. The definition is that the local overrules the global. So if you've defined a block flow under the whole model, that will be used and not the one defined under the control airbag. Global discharge, one of the last items in this presentation. A lot of words here, but let me summarize it. It's something like where you can store uncontrolled outflow. At least that's where it typically is used for. It can be used for uniform pressure and gas flow. And there are 2 types of outflow. Mass flow rate, and it is just simply subtracted mass from the airbag chamber, or by energy. Typically, it is considered as uncontrolled outflow, and for that the contribution in the total outflow shouldn't be that large. Typically, we say as a rule of thumb, if you just only focus on mass, shouldn't be more than 5 to 10%, because otherwise probably your design is not correct, unless you would like to have such an uncontrolled outflow. Heat loss. That's the last topic. Probably you remember a similar example from high school. You're sitting in a room, it's warm, and outside it's cold. Well, basically that is what's kappa. The temperature generally, depending of course what type of airbag you're using, is higher in than out. Well, due to this temperature difference, you will get an energy loss. Based on literature, a common value between 50 and 100 is sufficient. Sometimes customers use higher values for tuning reasons. That is all fine, but be aware that it has no physical ground. Let's move on to the last slide. It's about output. Basically airbag output, but also more general output. The reprint file and the log file contains error, warnings, and information about time step. Time step because of subcycling. Errors if you have modeled something wrong. Warnings might be very important, for example, if it considers extrapolation warnings. Suppose you have made a permeability function, but you haven't captured the whole range, and the last 2 points are maybe very steep or even negative. If you have extrapolation in those curves, you might end up with very strange results. So be aware for extrapolation warnings. In general it's relevant, but for airbags even more. We've seen examples where the temperature was even dropping to 0K, which is a bit fresh for an airbag, even for a cold gas inflator airbag. Also outputs like area. From your design you know what the surface area will be. Well, you can check that with the MADYMO results. Also for the holes. Are the holes really the area as you would expect to be? There are all kinds of animation outputs. You see 2 pictures at the right. The top is the forces applied by the airbag on the dummy and the steering wheel. And due to that you can analyze the load case transfer to the dummy, if you like. Or if something is not behaving as expected. It can also be identified in such a way. The lowest picture contains the stresses of the driver airbag. Clearly you can see here the shear effect. So the sine wave. Besides the animation and general output, you can focus on FE time history. For example, airbag pressure, volume, the temperature, but also the in and outflow. Maybe even you're interested to look at the rates of outflow. And for that you have to take the derivative in your post-processor, because that might give an indication where a large amount of outflow is occurring, which you might not be able to detect in the mass outflow itself. Molar fractions, heat capacities, so have you defined the proper gas properties? And maybe your kappa value of the heat is physically unrealistic. Also the airbag center of volume, maybe for OOP, jet velocity, reaction forces, all those can be requested or can be defined by MADYMO. Also multi-body time step. Suppose if you're going to validate your airbag by impactor test, well, you can define the output velocity or acceleration of the impactor. Obviously also the dummy signals. Also contact time history can be specified. And on top, or I should say at the end, the energy might be not that relevant, but typically the energy balance is used to check the robustness of your solution. The total energy, obvious, has to remain constant. If you see large spikes or noise in one of the total energy functions, maybe the total, but it can also be in the contact, and then it might be an indication that there is not something wrong, that there is something wrong in your simulation. For that I consider the energy balance as a good way to check the robustness of your simulation. I would like to emphasize or to make you aware that on the TAS International website you can find modeling guidelines for air, uniform pressure and gas flow as well. You can download them for free. This is the end of this presentation. Goodbye.